The Jones polynomial was discovered here in this office in 1984, and that was really a pretty exciting time. So maybe you'd like me to tell you a little bit about that. When Jones came here to talk to me, he had found representations of the braid group, matrix representations of the braid group. The entries in the representations were polynomials in a single variable. He knew that braids had something to do with knots, and he was interested in knowing whether there were any applications of his representations of the braid group. So he came here perhaps 2 or 3 times, and he told me about his matrix representations, and I told him about knots and links. Then one day we looked and we realized that one of the things that is a piece of the relationship is that the link type doesn't change if you stay within the conjugacy class. Well, his matrix representations had trace functions, and we all know that traces are class invariants. And one day he realized that with just a small modification, his traces could be made into link invariant. So he came here that day and he said, well, here's this invariant, let's calculate it. So he said, what's the easiest knot that I can use? Well, the very easiest example you can find is a trefoil. It turned out that it was t plus t squared minus t cubed. Well, there was another polynomial around that's also an invariant of knots. It's the Alexander polynomial. And the Alexander polynomial for this knot was known to be t inverse minus 1 plus t. Well, this is Alexander. That's Jones. Well, there are 2 trefoil knots, and one is obtained by looking at the other one in a mirror. And in fact, these 2 knots are different, and it's very hard to tell them apart. The argument that was used way back in the 1930s was extremely long and clever due to Max Denning. But as it happens, their Alexander polynomials are the same. So the next question was, why not calculate the Jones polynomial for the left trefoil? And all this happened in about 5 minutes. Well, it turned out to be t inverse plus t to the minus 2 minus t to the minus 3. That is, each t is just replaced by a t inverse, and of course these are not the same. So immediately it became clear that either these 2 polynomials are really different or there's a mistake. Well, there was a very easy way to begin to check that, and that was to take a look at the figure 8 knot, because as it happens, the figure 8 knot and its mirror image are the same. So we calculated the polynomial of the figure 8 knot, and it turned out to be t to the minus 2 minus t to the minus 1 plus 1 minus t plus t squared. Well, on replacing t by t inverse, as you can see, since this polynomial is symmetric, in fact, it doesn't change. So in the space of about 10 minutes, it began to look like not only is this something unusual and interesting and because it came from a different place, but in fact, it looks like it's different from the Alexander polynomial. So by the end of that day, we had calculated a lot of examples, and the polynomial wasn't missing a beat, and it was pretty clear that it was new and that it was correct. And when I went home that day, I thought, I couldn't believe it that there was another polynomial. It wasn't the Alexander polynomial. It was really different, and it opened up a whole new world of mathematics, and it was very exciting.